All right, let's start the lecture. And it's going to be a recording with not a lot of people compared to your usual. 10 people in this room, yay. All right, online folks, can you guys hear me? All right, awesome, let's move on. So today, let's continue on from Tuesday and talk about scheduling. So we wrap up with this technique we call shortage of first scheduler, right? And I compare this to like when you go to a supermarket and it's like that one line with like less than 10 items, right? The way it works, the thought process is the same way. If my job is short, there's a benefit for the whole system for letting me through. Because first of all, I don't have to wait that long. Second of all, it's avoiding convoy effects, which means that I have a big job and then a bunch of smaller jobs after me, right? The example here is, let's assume the same A, B, C processes, right? And B and C take 3 seconds and A take 24 seconds. In this case, B and C would get scheduled first because the job length of B and C is 3 seconds, which is a lot smaller, right? So the benefit is this is optimal in terms of minimum wait time. I want to get the smallest wait time for all my processes, then shortage of first works. The trade-off is the first thing, how can I predict the future? So let's throw some ideas. If you are the computer, what can you do to predict how long am I going to run for? What are the possible information can I use? What do you mean by the size? That's a good idea, but what do you mean by the size of the process? So basically what you say is like, hey, let's store the size of what the process has to run, right? But what do you mean by the size? Like, is it the process last job or what? Okay, so your idea is let's store how much area, like how much memory the process needs, right? Because I guess your reasoning is if I use a lot of memory, it's likely to be a long process. It's likely to run for a while, right? Actually, that's a pretty nice idea too, right? What else can I do? That idea might work actually well, to be honest. But yeah, what else can you do? Because I'm trying to get at something here, right? How about, because when I run a process, it's not like I run everything in both, right? I will run in burst. I have the CPU burst and the IO burst, right? So one thing I can do is, what if I keep track of the history? The last time I have the CPU burst, I ran for 2 seconds. The last time I ran for 4 seconds. And I keep track of this, and I use that to predict how long will I run in the next burst, right? How many people think that that can work? Okay, great question. It might work, but what about the first time I run this process, right? So that's a great question, because the first time you run the process, you have no information, right? I mean, usually one thing you can do is like the first time you run, you can do first come, first serve, round robin. Basically, this process has been waiting for a while, let them get the turn, right? But that's one great design question, because the first time dictate everything, right? But if I use the time, and here's the idea, let me keep the history of all the time I used so far, and I use some kind of average, right? So let me ask you the follow-up question. Which one would matter more? The last time I run or the last long ago that I run? Which one is likely to be more relevant the last time, right? So one thing we can do is we can try to use this alpha value to multiply. Basically, T is the actual length, tau is the predicted length. So here's my prediction. My prediction is going to be based on the alpha value of the last time I actually run, right? And then I use the exponent average that keep going down and down and down and down the longer I run. That's also the preemptive version of shortage of first. We'll talk about this later. Let's talk about the predicting the burst, right? So here is the result of the guess that I used. If I use the equation earlier and the alpha value is 1/2, basically the last time I run, I'll have the weight of 1/2. The last two times I run, the weight becomes one quarter. The last 3 times I run become 1/8. So it goes down and down and down. And as you can see, the actual time I run is like this, right? 6, 4, 6, 4, and then 13, 13, 13, 13, 13. The running average become originally is 10, then 8, then 6, then like 5-ish, right? And then go back up. Because when you start to have longer runtime, this running average will go up with that, right? So this can be somewhat helpful on predicting how long am I going to run, right? On predicting how long am I going to run. The question is why exponent average, right? Basically, this gives more weight to the recent epoch, the last time I run. So if alpha is 1/2, basically the equation becomes 1/2 t of n, 1/2 multiplied by 1/2 t of n minus 1, 1/2 multiplied by 1/2 multiplied by 1/2 t of n minus 2, and so on and so forth. Basically, it's alpha, always alpha is being multiplied. And then the term afterwards, 1 minus alpha to the n, from 0 to whatever n you're trying to predict. If alpha equals 0, right, is basically, I don't count any recent history. And if alpha is too big, oops, my bad. If alpha is 0, I don't count this guy, right? Because it's alpha multiplied by that guy. Alpha is gone. Alpha is gone everywhere. So history doesn't matter. If alpha is 0, its history doesn't matter. If alpha is 1, 1 minus alpha is gone, so you always just go with the last time you run. See, this is alpha multiplied by t of n plus 1 minus alpha to the something, right? This always go to 0, so you just only count the last history that you run, the last time you run. Sometimes we call this last time predictor as well. Let's say the last epoch I run for 4 seconds, I predict 4 seconds. Sorry about the typo. Basically, the last time I run, I just only count the last time I run. All right. Now let's go a little bit deeper here because I would like to follow up on the answer that say, hey, why don't we just look at something else as well, like memory footprint? How much memory I allocate? Why does that matter? How many of you write code this way? I have a for loop, and then another big for loop. And then the way it loops around, maybe like going from here twice, and then go down here, run it a few times, go back here. It's like nested loop. But inside the big for loop, you have like 5 more for loops. Right? It means that sometimes my history also doesn't matter because I'm in a different section of my code already, right? So this can happen as well, right? Again, predicting the future is hard. This is like one attempt to predict the future. That's why I said, hey, that might be also a good idea. I look at how much memory I allocate right now that can predict or give me some possibility of how much time am I gonna run for. Because if I allocate 1 million array entry, any sane programmer would use all 1 million of them, or something like that, right? So they are likely to do that. So that might be a good factor, right, into your scheduling. The other option is I use shortage of first, but I have epoch. Basically, I use shortage of first, but I can preempt any running process. I can preempt any running process. So let's say A arrive at time 0, B arrive at time 2, the same thing. A run for 24 seconds, B run for 2 seconds, 3 seconds, and C run for 3 seconds. This policy will do this. Whenever new job arrive, I will check the estimate runtime. If it's lower than what I'm running right now, I preempt the running process. So here's what happened. A run for 2 seconds. Nothing arrived so far. It's only A in the system, so I run A. Then B comes in. What happened? How long does it have to run to finish? 22, right? A needs 24. I ran for 4, so it needs 22 more seconds. Which one is lower, 22 or 3? 3. So the system context switch run B for 3 seconds, and B finish. Obviously, now it resume A. Now at second number 8, C arrived. What happened now? I switch, right? I run C for 3 seconds, then I finish A. The average waiting time is what? Does they have to wait? Okay, B and C obviously doesn't have to wait. I arrive, I get to run right away. Right? And A, you don't have to wait to get service. And also, if you look at the turnaround time, it's only 30 seconds. Turnaround time for B is 3 seconds. Turnaround time for C is 3 seconds. So, yeah. A wait for 6 seconds, basically, because every time B and C arrive, I have to wait to keep going, right? Now assume the same example, right? But C arrived at second 26. What happened? In this case, A just need 1 more second left to run, right? Because A run for 2 seconds, B then run for 3, then A keep running. At time 26, A only have 1 more second to run and finish. So who has shorter job, A or C? A, right? So in this case, I'll keep running A, because even though C arrived here, I need 3 more seconds. So I have the better for the system is C wait and then run afterward. Because I mean, what's the point of A waiting 3 more seconds? C only have to wait 1 more second. That's it, right? So that also, this is like assuming, first of all, assuming you can preempt somehow, right? Some system you cannot preempt, some system you can, depending on the assumption of the system. If you can preempt, and what's another important factor that can impact the overall runtime that we haven't really talked about? When I context switch, what has to be done? Yeah, I have to store the context and then switch the context, right? So that also takes some time. So if you do this really often, the time it takes to do the context switches will start to dominate. So this, from a theoretical point of view, this looks really nice, right? But this might also cause context switching to happen quite a bit. So you have to consider that as a factor as well. How many people here heard about serverless computing? All right, so what is, okay, so, but you all heard about cloud computing, right? So when you want to deploy something to the cloud, right, you would need, let's say, back-end engineer to deploy the, say, container or virtual machine to configure the system, and then, hey, I'm gonna configure it before I deploy. I will configure everything. Serverless is another way to think about cloud computing, but say, hey, I just want to run the function, and I don't care how I configure the system. I would just not do it. I just want to, this is function definition. I want to run it, right? And magically somehow the system will handle the rest. The thing is serverless. More than function call will run for like microsecond or millisecond latency because your function call is a lot smaller, right? It's not a full-blown service. It's a few functions, and you run tons and tons and tons of those function calls. Now, when you look at micro scale, context switch really matter. right? Context switch really matter. So right now, when serverless computing actually is becoming one of the possible trends of cloud computing going forward, there's a lot of push as well on how do we design the system for serverless, because we never think of it this way, right? 3 seconds to run job A, right? Context switch maybe 10 microseconds, does it matter? No. 10 microseconds within 3 seconds is like really small. 10 microseconds within 1 millisecond, that's getting bigger. That's like 1% already, right? So on the theoretical side of things, this makes sense. But then you also have to consider what are you running on the system. There's also this thing called priority scheduling, because each job doesn't look the same. If I say something, if I say I want to print a PDF document, I don't care when it's gonna be finished. If it's finished 1 second later, that's fine. My printer cannot even handle printing in 1 second, so 3-second delays doesn't matter. Process has priority number. So one thing the CPU can do is I can then allocate the highest priority process first, right? Then I use shortcut first to perform priority scheduling. This is, if I want to use shortcut first for everything, right? I can set the priority as the inverse of predicted burst time. If I have high priority, the size of the job gets way smaller from the point of view of SJL. The problem here is starvation, because eventually if I have a lot of things to run, my printer will never get my PDF document because it's a likely lower priority, right? So solution, we call this aging. Basically, as the process gets older, we give them higher priority. All right. So the other thing we talked about is already, context switching is not free. All right, be aware of that. Scheduling that switch a lot of process in and out and in and out, you're gonna have context switching overhead to dominate. Because I guess it will start to dominate the runtime, right? We also we'll talk in module 3 when we talk about architecture. I'll talk a little bit about hardware multi-threading in more detail as well, on how to make context switching almost free by the hardware, but we can only maintain like 2 contexts for the CPU, way more context for the GPU. We also can look at multi-level queue. Multi-level queue means that I have a ready queue for a different type of processes. For example, one way I can break it down is a foreground process and background process. Foreground is interactive process, background is batch process. Things that I just need to run to make sure the system will work, versus the foreground process like your game that you're running right now, right? Each queue would have its own scheduling algorithm. For foreground, round robin make a lot more sense because each one has to take turn to run so that the user doesn't feel like things are slowing down, right? I mean, what if you run Spotify? You're listening to music interactively and then somehow you never heard your music for like 5 minutes because of starvation, right? So round robin in that case make a lot of sense. Then background, we don't care. First come, first serve is also okay, right? We can also kind of figure out, do we migrate? For example, sometimes we switch the background to foreground back to background, right? Who get to use how many? Also for the foreground process, how much CPU time that I want to dedicate to background? Because foreground and background both compete for the CPU. Would we do maybe 80% foreground, 20% background? Would that work, right? So those are another knobs in the system that you can tune and can change to make the right trade-off for your system, right? One sample of this, for example, right? I can make it this way. System process has the highest priority, followed by interactive process. Because system process, if it doesn't run, your machine doesn't work. Then interactive process, then interactive editing process, then batch process, which is background processes. And then I deprioritize anything you guys run on this skill. Maybe, I don't know. Doesn't make a lot, yes. In interactive, like in a case, like let's say I change interactive process into two categories, right? The interactive process that you are interacting right now and interactive process where is editing something, like is modifying something on your computer, right? In that case, you can have different priority because interactive process where you're not modifying IO, right, might have higher priority. And then student process, yeah, no one cares. Which, again, as I said, might not make sense. You might want to schedule them as an interactive process because you guys are actually editing, for example. A process can move between each queue as well, right? For example, aging. If the process wait inside the batch process for a long time, maybe I promote them into interactive process. Even though they're not interactive, I should put the process in the queue, right? So multi-level feedback scheduler is defined by, first of all, number of queue. The scheduling within each queue, because I can use round robin for one queue, first come first serve for another, shortest job first for another process. The method to upgrade, move up to higher priority queue, or move down to a lower priority queue, and the method to assign the queue to the process that needs the service. Like a new process, for example, where do they go, right? An example on the exam, I can ask you, here's one policy I have for the system, might make sense, might not make sense. And here's the number of queues we have. This is the policy. And these are all the processes that happen at these many seconds. At second time 3, this thing arrives, time 4, this thing arrives. Run it. One possibility is, let's say we have 3 queues, right? And I say every new process go into the first queue. The first queue I do round robin with 8 milliseconds, means that everyone takes turn running for 8 milliseconds. Then the next policy I can cook up is, if it doesn't finish, move to Q1, lower priority. Also round robin, run for 16 milliseconds. If 8 plus 16, that's 24. After 24 milliseconds, if you're not done yet, go to the last lowest priority process. And then the policy across all the queues is, if the first queue is empty, then you run the second queue. If the second queue is empty, then you run the third queue. Basically, if there's something in the first queue, keep running that first. That can be something I cook up, right? This is a valid policy. Would it work? Maybe. Well, it will work. Does it make sense? Maybe. Because I haven't really talked about aging back up. Let's say I'm in the first come first serve for like 5 seconds. What do I do? Maybe I want to promote it back, put that into the first queue, right? There are many other factors, as I said, like as you suggest, for example, when we look at memory footprint to predict, right, the size of the job, right? Real system is also complicated. It's not just about wait time. It's not just about response time. It's like all these things together. Then you have to think about even things like, if you run Amazon, right? If you pay more than the other user because you want better priority, how are you going to enforce that in the system to make sure it looks fair? To make sure it looks fair, again, looks fair for everyone. For everyone, including the guy who pays just a little, right? If I pay a little, well, I'm okay being deprioritized, but if the guy that pay a lot never get that priority, then that's not fair. Also, like, how would you define fairness? There's even thing like this. Have you ever run through the case where you're searching for some term and it takes longer than usual because that terminology, like, not many people search for it. It can happen, right? Sometimes we call this like The extreme of this is like what we call like 95th percentile latency or 99th percentile latency. If I rank the response time for all the process, have I look at the 99th percentile and have I ever serviced those guys? Because those are important as well, right? Those can be important as well. So these things are important to the system. Another example is like, hey, what if I can just schedule and from the user point of view, they never notice anything wrong with it. Then if I know I can turn off the CPU, I turn it off to save power. That also makes sense for your laptop, right? If you're okay with your laptop performance right now, I will throttle to make sure the CPU gets slower. Because why not? I save power, my battery lasts longer. Right? These also impact scheduling. What do I do in the hardware? There are many more things to discuss, like mobile phone. Mobile phone interactive jobs are way more important because you only have one thing on the screen, and that's the only thing you look at, right? Desktop, many more interactive jobs, many more background jobs, and typically, unlike mobile phone, you have enough memory. There's so many optimization in the I/O that you can do to make sure that file access is faster using the memory, for example. In a data center, there's not a lot of interactive process. People just submit a job and wait for it, right? But then also latency, like if you submit some, like for example, remember how like the mall prompt system like went down on the first day they launched it, right? When the first day we got the vaccine, right? That's a really poorly designed thing. But they know how many people are gonna get vaccinated that day, right? That shouldn't happen. Or that's kind of like when you deploy a data center and you have to update the database, right? You need to know how many concurrent users are gonna do that. And for each hospital, you know how often can you vaccinate and update, right? Which is maybe one person every 3 minutes. Means that for every machine in the hospital, I will update one entry in 3 minutes. I multiply by how many hospitals I have. I multiply by the size of the update. I multiply by the number of computers that the hospital have. I know the demand. Why can't they do that? Right? You need to be able to do this because it's actually if you boil it down, this is simple. Let's say a request would have to update a row with the patient, right? Then you can calculate the size. Then you know how long the job would run, right? So that's the data center kind of setup, right? Supercomputer, this is a little bit different from data center. Most of the time, when you look at supercomputer, people still share them, but it's actually more time slicing. It means that if I use the machine, I will make sure only me can use the machine at the time, then I'll yield it back to someone else. And what, like for example, the Thai Supercomputing Center, will kind of partition their machine into different bulk of CPUs assigned to each user, and they guarantee that they're gonna get that bulk, that many CPUs to run at this time, and then they context switch the whole thing, run another job, right? So throughput is way more. Well, both of them cares about throughput, but the context of supercomputer is like actually quite important for the workload because they demand throughput. Cloud running serverless, I talked to you about this already. Like the function call is microsecond, so context switch, the overhead from the OS get way more and more. Hardware also gets better. This is another thing that changed quite a bit today. Hardware gets better. Your disk gets faster. Your network gets way faster. We have the GPU that we can use to program things. That means the compute gets way faster. Oh, not faster, but more throughput. Sorry, because I work on GPU. I actively design GPU as my research. I need to tell the truth. It's not faster than CPU, but you get more throughput. Okay. You have also tiered memory. You can use a fast but small, and then there might be this a little bit slower, but can have like terabytes and terabytes of memory. One technology of this is Intel Optane. You might have not seen it yet, but basically it can support a much bigger, a new type of memory we call non-volatile memory. It's not the SSD. The way it looks like the SSD, but the way it operates is way faster than SSD. We use that as memory. Data also shared everywhere. If I run something on the GPU, they actually compute like machine learning workload that you run on the CPU, but you ship it to the GPU, right? So that's data sharing from two different entities. GPU has its own memory, yay, fun, right? So scaling matter now. Scaling also matter for both of them and for the whole system, which consists of two of these, right? We also now have more accelerator, like your mobile phone, what we call system on chip. The reason why we call it system on chip is your phone has a CPU, has a GPU, has machine learning accelerator, basically anything that has to do with matrix multiply and machine learning basic operators get shipped there. You have the signal processing accelerator to do like processing your camera signal, process the audio signal. You have your modem, right? You have the accelerator that might have to do with data compression to make sure everything is compressed within, right? Scheduling also now get complicated. You on the data center side, there's new type of thing. I can do processing in memory. I can use FPGA to accelerate. For example, if I want to run a firm for high frequency trading, people use both the GPU, the ASIC, which is hardware designed just to do that task, and FPGA to make sure I can run whatever I want to run as fast as possible. Because in high frequency trading, if I'm the first guy, I get rich. Yeah. Some more recommended reading, definitely not for the context of like your like junior year kind of where things are, but I found these quite interesting. The first is the paper called The Attack of the Killer Microseconds. This paper talks about, and from the communication of ACM, so they kind of boil it down so that things are easier to understand, not a lot of like super technical detail. There's also a YouTube for the talk. It talks about now that the hardware changed. Things that we consider to be like, okay, this usually takes too long, get faster. What's the effect? Because now your system can be impacted by these things. So you might have to redesign both the hardware and the system. The second one is from Moore. She is a professor at CMU. Fun fact, for all the classes I've taken so far, she is like one of the top tier in terms of teaching. You know, like professor when they're really good at teaching, right? She's one of them. She has another, I'm not sure if it's a paper or there's like another title as a paper, but there's like a technical report on arXiv, which is talking about how do you schedule under real world constraint, which some of these will follow up from the discussion we have today, some of your suggestions, like what if you look at footprint and things like that. Feel free to check it out. She also posts quite a few videos on YouTube that she is one of the world experts on scheduling. If I have to point to people who do scheduling as their main job, she is one of them. All right, any question before we move on to protection and security? Shall we do 5 minutes break? Okay, let's do that. Okay, so what should be the goal of enforcing OS protection? Basically, in the protection model, right, I want to first abstract away my computer into a collection of objects, hardware, and software. Objects, hardware, and software. And each of these objects will have a unique name to that and can be accessed through a well-defined set of operations. For example, your home directory should have some form of protection. No one else should be able to like write something to it or read something from your home directory, right? And the goal is I want to make sure that all my objects are accessed correctly. And only by the group of people I allow them to do so. And that's it. That's a high level goal. How many people think it's actually impossible to do? It's actually quite hard to, yes. It's actually impossible to do. But you can do our best to make sure the effort for someone to destroy this assumption is really, really, really hard, right? So one of the principal protection, right, is the what we call the principle of least privilege. It means that if I have a program, right, the user inside the system should be given just enough privilege to do that thing. If I have the students in the server, they should be allowed just enough ability to code your program, run your program inside your home directory, and that's all, right? Properly setting the permission can limit the damage, and it can be static or dynamic. For example, I can have permission that happen for the whole lifetime of the system. I can have a permission for the whole lifetime of a process. Okay, I can change by another process as needed. What sometimes we call this domain switching or privilege escalation. How many people use a sudo command already? Yeah, that's kind of escalation from yourself to like root permission to do something, right? And there's also this thing called granularity of protection. You can have a rough grain, like it's really simple. No one can touch this directory. No one can go into the kernel land from the user, right? It's easier to manage and it is done in large chunk. And you can make it fine grained like a file access control list or the role-based access control. Basically, these are more complex and depend on the system and how they would implement these things, but are more protective because you have more information on who can access what. And the domain of protection can be from the user, from the process, or the procedures. And you can also have the option to have a really nice audit trail, right? This is, think about it as the same as when someone audit like your company. I look at the recording of all the activities related to protection and see if it's done properly or not. In Multics, for example, it's like a ancient version of OS, right? You can look at this what we call protection ring, from ring 0 to ring 1 to ring 2 to ring n-1, right? And these are the domains. Basically, the key idea is if I'm in the outermost ring that includes the innermost ring, it means that I'm part of the domain inside, but not the other way around. Think of it this way. I have a hierarchy of protection domain. The top of the hierarchy can access everything. The second level can access anything onward. The last level, I can't do anything except for my level. All right. What's the benefit of this? Quick question. Is it simple? Yeah. This is actually quite simple, right? And the ring of protection separate the functions that we can do into the domain and now order them in a hierarchical way from the most privileged to the least privileged, right? And the computer is treated as just process and objects. And objects will now include both the hardware objects like all your device, disk, network, and things like that. Into the software object like the file in the disk, the program, and the semaphore that you can use. And this done in a need-to-know principle. Need-to-know principles. The process should only have access that it just required to finish the process, and that's all. So that's the principle. Again, principle is not the same as reality, right? in reality, the way you implement this principle can vary on how you would like balance the trade-off, how many rings you want to do, how would you impose a protection, how would you avoid people cracking into this thing. The implementation itself can require, first of all, the specification of resource. So I need a list of these are all the resources I have to protect, right? And then the set of objects and the types of operations. So objects and things I can do to that object. Objects like file, what are the things I can do to a file? I can read, I can write, I can copy, I can download. I mean, not download, I can run, right? For example, the access rights becomes, now that we simplify things, I have objects and I have things I can do. Access rights means that I tie the object name with the set of rights. Rights are the ability to do the operation on the object. So it's basically object, things I can do with the object. All right. And now that I have access rights, domain can share the access rights depending on the domain. Right. For example, I can have file A, access right to be read and write. Now domain one, which is kernel, for example, can read and write to the file, and the user can also share the same rights, which is read and write to the file. And the association can be static or dynamic. If dynamic, again, think of sudo, I can domain switch from my user to root. Yay, right? And the structure of the domain is the right set. Again, remember access rights, right? Access right has object and things I can do to the object. So that's one access right. The right sets are the valid operation that I can perform on the object. Domain is just becoming a set of access rights. Each domain will have a set of access rights that the domain can do. Are we done? Yeah, somewhat, right? Now we classify, for example, different user into domain. And one user can have multiple domains. For example, I can be in the user level. I can have in my own group, like my username, right? And then each domain has its own set of access rights. If I'm in this domain, this is what I can do. If I'm in this domain, it's different things I can do. And this is exactly what I just meant. Again, domain can overlap, right? In here, domain one have access, read and write access to object 3, read and write access to object 1, and execute access to object 2. Domain 2 has the write access to object 2. They share the print access to object 4. Then domain 3 also share the same object 4, print access, and then execute access on object 1, read access on object 3. Right? And to simplify things in Unix, what's the domain? User ID, right? That's the simplest thing you have that identify the user, right? So why not? And domain switch can be done through the file system, right? Each file is associated with the domain bits. Each file will contain the bits for each user ID. If the bit is set, basically when the file is executed and set user ID, if those are on, for example, it means that that user ID can execute. If the file has the permission to execute on this user ID, it means that that user ID can run the file. So the same thing will go for read and write and other operations. Depending on what are the possible operations on that file or on that object. And the user ID is reset when the execution completes. And domain switch can be done through, for example, using password. How many people use the su command to change the user? Oh, I don't think you have for the syscube because you cannot. But you can, for example, do the su to change to root on your system. That's the next thing it asks for is what's the root password, and you put it in. So when you give the password, this secret code become the ability to allow domain switching. You can also use the command like sudo to domain switch. Now, if you think about it, right, this set of access, right, we can think about it as a big matrix, right? For all the objects, these are the things we can do for each domain. It's a huge table, 2D table for all the objects for each domain, and these are the things I can do. The entry will become things each domain can do on that object. We call this the access matrix. The row represent each domain. So let's say that 3 users on your computer. User A, user B, user C in a row. The column represent all the objects in the computer. Now you can have the entry become what are the operations I can do. Here's one example. I have 4 objects, F1, F2, and F3, and the printer, right? And 4 domains in the case, maybe 4 users, 1, 2, 3, and 4. User 1 can read F1, read F3. User 2 can just print to the printer. Maybe this is like a printing service, right? Which allow domain switch from the user call domain 2, say, hey, print this. Any questions so far? All right. If you have a question about how do I implement this thing, because this thing seems like a lot of overhead, yeah, we're about to go there. All right. So for the process in domain DI, try to do an operation OP, it must be on the access matrix. This is kind of formalizing the definition. If I can do that operation, it means that on the access matrix, that operation has to exist. User can create objects that define the access column for that object. Let's say I create a new object, right? I can then define who can do what. And it can be expand dynamically. Basically, I can keep expanding this. I can set the owner, I can set the copy, control, or transfer. Transfer means I switch from domain I to J. Control means domain I can control the other domain's access rights. For example, root domain can control any user's access rights, right? Copy in the table, you have the asterisk, means that I can copy from OI to OJ. Copy and owner are applicable to objects, and control are applicable to the domain's object. So this allows the separation of the policy and how I implement this. I have an access metric. It just means that this is a policy. I can do these things. And then it's the job of whoever has to program this whole thing to implement it. So I can design how I want the policy to be. Another set of people can design, okay, how do I implement the access metrics? All right. The OS enforce the rule. The OS enforce only authorized agent can do that. That's the mechanism side. The OS enforce the implementation of the access metrics, and the user dictates the policy. Because otherwise, I have this. Would the user have to access the have to implement the access rights, and also how to build the metrics, how to enforce the rule? That's not good, right? User should not be able to enforce the rule, so we just let the OS handle that. It still doesn't solve the general confinement problem, or it means I have to prevent leakage of information to other programs. But we're going to talk about this more in the security part of today's lecture. All right. So here is how I can implement things. Again, each column is objects with the access control list, right? Each row is a capability list. The row is like, these are the things I can do. I can do, because the row is the domain, right? So I can build it this way. A huge giant table. The row is the domain. The column are all the objects, including the domain here, because I can have switch operation. For example, D1 can switch to D2. D2 can switch D3 and D4, and D4 can switch to D1. If you have a root user here, it's like switch. I can switch to anyone, right? Yes. I switch the domain. Basically, think of it as I switch the user from domain 1 to domain 2 to domain 3, for example. You can have copy writes, for example, here, read star and write star means that I can copy that object. That, like, with the asterisk means that I can copy that object. I can make another copy. So it can look like A and B, the same thing, right? You have, I mean, the only difference down there is like I have another read in D3 because I copied to D3. I copy the access rights. I also have the ownership that can be assigned. So in this case, one more new thing, who owns F1, who owns F2, and who owns F3. All right? Yes. So when you assign the rights, the user do that. Because the user, now that you have the ownership, as you can see here, right? Originally, F1 can be executed by D1 and D3. But D1 is the owner. I can say, hey, D3, you're not allowed anymore. F2, because D2 is the owner, now I can assign write copy and then copy the write permission here. Right? So with this assumption, the owner can do whatever it wants to do, and it's only one single owner, which is nice, right? For this. All right, implementation. One thing I can do, metrics. 2D metrics. What are the downsides? I have a global table, 2D table, right? Everyone can access that. It's probably a big metric. So one of the big downsides, this table can be huge because in your system, there's a tons of file, right? So it doesn't, it's more than it will not fit in memory, right? And also difficult to group objects together. Yes. The table. Oh, again, the OS apply the actual action to the table. The policy is done by the user, and the user tells the OS, hey, can you do this? Then the OS sets the permission. Yes. The OS will check the table and it would enforce that I can't just randomly access the rights. But it's seen, the table is seen by everyone, so everyone has its rights. Louder, please.
What is protecting the tables from?
Oh, you talk about hacking, no? depending on how you attack, right? This can be attacked. And everything we talk about, as long as it's in the memory, as long as it's in the software, it can be attacked if you're not writing it carefully. Even though when you write it carefully, it can still be attacked.
Like, no point in worrying about it. Yeah.
Well, we will do that later. We'll do that later. Yeah. So the second thing we can do, right? We can maintain for each object, I have a list. And that list contains what? The domain who can do whatever with that object and the right sets. Why? If I am trying to access this object, I just go through the list, right? And see, hey, do I exist in the list? If I exist, what can I do? If I didn't find myself there, the OS will say, hey, you can't do something with that object. These also can be easily extended to contain a default set. A default set, which is basically, let's say I create a new object, what would be the default? For example, you create a new file on Unix, right? You become the owner. So that becomes like a default thing to do. The option 3, now I have a list for the domain. So instead of a list for each object, which can have tons of lists, right? Now I have the list of the domain. Domain contains the list of objects and the rights. So instead of having each object has a list of domain and the rights, become the domain has a list of objects and the rights. The nice thing about this is if I'm a user, I don't have to search the object list. I just search my own domain list and see what are the objects what are the list of objects can I access, right? So the last thing we can do, we can use lock and key. It's kind of like a compromise between the two because you have to walk one way, you have to walk the domain list, the other way you have to walk the object list. None of them are nice because walking the list means that you go through a bunch of things, right? This is a compromise between the two designs. Each object has a lock. Each domain has a key. If I have the key that matches the lock, I can access it. This is kind of like instead of maintaining a huge table that are a bunch of empty cells, because I mean, if you look at the table, there are going to be a bunch of empty cells. Now it becomes like each possible entry has one single key and one single lock for the object. If the key match, I can go in. That's it. All right, and that's it. Yes.
One has a single lock.
So the object will have a lock that only work with a certain set of keys. The domain will have a key, only one single key that because you just have lots of that contain the list of possible key that can go in. So any domain can just assign a unique key. And if the unique key can go into the lock, means that you can access it, right? This eliminates what? If you look at this giant table that's filled with empty cells, right? It eliminates the need for you to maintain those empty cells in memory. Because you just maintain the lock and maintain the key, right? That's it. Okay, so you see 4 different ways to do this. That trade-off, right? Global table, simple but big. Access list, there are many objects and many access rights, so this can be slow because you have to walk them. And then you have to kind of figure out what are my set of access rights. But the first time you access an object, it's simple to add things in. And then if you want to revoke any rights on certain objects, it's simple because you don't have to walk through every single domain list to revoke the rights. You just go to that object and say, hey, that object doesn't have this right anymore. Take it out, take it out, take it out, take it out. Capability is useful for localizing information when you have a process, because the process belongs to a user, right? Because the process belongs to a user, now it's just going through one list. But when you want to revoke the capability, if you want to revoke, hey, this file process domain 1, 2, and 3 cannot access anymore. What does it mean? I have to walk every single list domain to go to that object, then to revoke the access. Lock and key are typically effective and flexible. I can revoke any key because if that user should not use the key anymore, get rid of it. And I can pass the key, one domain can pass the key to another domain. So it can be quite efficient, right? In a real system, in Unix, for example, we have the list of, it's a combination of the option 2 and 3. The first time you access the object, you search the access list Option 2, search it because the first time. Then after last access, you destroy the capability, right? If allowed, then you create the capability list and attach the list to the process. So after you attach to the process, now you have the option 3 for the process. New object that get created will get attached to the process, and when you're done, you just destroy the process list. Now for the access rights, there are many ways to revoke them. You can do it immediately. You can delay them until someone accesses it. Like think lazily revoking. You can be selective, just this one, this file, or you can be generic, this whole group. Partial or total. Partial means that instead of read and write, I just do read only. Total means that no one can access it anymore. It can be temporarily or permanent as well. So these are options that you can do, and you can implement them in the system. The access list, to revoke, just delete the rights from the list, which is simple, right? You just go through the list, remove the entry, and you're done. For the capability list, if you have to revoke, again, capability is when each domain has its own list. Each domain has its own list. All right. If I have an object that I want to revoke the rights, I have to walk that list for each domain because the domain can share the object rights. So I have to walk all of them and say, hey, can I access this? Can I access it? And revoke them all, right? So you can do a reacquisition, basically periodically delete with the requirement that if it's revoked, I deny access. I can set a pointer from each object to all capability. These are like implementation. How can I do this, right? I can have back pointer to the object. Basically, for each entry in my capability list, I have the pointer to the object. That would point to the other domain, so I can go and delete them. Like shortcut. Think of it like back pointer becomes a shortcut to like another entry I can delete from the other domain. I can use indirection. I have a global table, and then the capability point to the table. And I can use a key where I have a unique bit pattern that associated with the capability, like RWX bit. Then I have the master key. If the key match the master key, I can access, and I can revoke the whole thing by reassign the master key. I can have a role base, yes. This for capability of option 3. Option 3. Option 3, but I want to be able to revoke the access. Then I use the master key technique by saying if my key match the master key, I can go in. If I can go into that object. So the object has the master key. If I want to revoke the access, I just change the master key because then every other key will not match anymore. And think of master key as like random bits. 1 0 0 0 1 1 1 1. If it match, good. If it doesn't match, cannot access. So role-based access control, or RBAC, this protection can be applied for non-file resources, right? So Oracle Serverless 10 provides this capability basically for the user. Let's say you're looking at user run role 1, right? I would implement the property of the least privilege by assigning the privilege to the role. And if I have the privilege, then it's assigned to the process. Basically, I can then assign the process the privilege. Now the process has the privilege assigned from the user. Then I can grant the privilege to the program by giving the password for the role. This is kind of like how the Oracle Solaris can implement the access metrics. So for each user, they have the role and the list of privilege. And the role can basically transfer to my process. And then I can use the password to expand my privilege. You can also use mandatory access control in, I think it's in Apple. So basically, traditionally, the OS has what we call DAC or discretionary access control. It limits access to file and object. So this is a weakness. If I'm a user, for example, I need to get elevated to admin to do something, right? I need permission to do something. Mandatory is stronger. The resources are not accessible except for the intended owner. Even the root cannot circumvent this. It's not accessible except to the intended owner with the S at the end of the owner. We have multiple owners. All right, yes.
What's discretionary?
It means that I can elevate myself to become another role and access that guy. Over here for Mac, it means that I need to be assigned a part of the owner. Otherwise, I can't access it. I can't elevate myself to the root to access the file. Yes. That's a trade-off. So basically, you're trading off security with like the possibility of I screwed up the access, right? Right. So basically now I assign label to objects and subjects. This includes process you're running. Okay. And when subject requests the access to the object, again, subject requests access to the object, we check the policy. We check the policy. If I have the ownership in the label, I can do that. If I don't, I cannot. Oh, sorry about, yeah, macOS uses this as well. So basically, we use a mix of the two. We use a mix of the two. Super important secure, like optional config for your machine, Mac. You better be the owner to fix it, right? For normal objects, use that. I can elevate myself to install program, for example. So modern OS uses like Trust BSD in Mac OS, Trusted Solaris, SE Linux, and even Windows Vista, right? Back in the day, use Mac. So for SE Linux, again, here I have a subject, right? And subject like a process want to do something like read a file, right? So SE Linux will come in, the security server will check, and it has a database of the policy. So it checks the database, hey, can I do this? If I was granted the access, I can then access the file. If I do not have it, I get the deny message back saying I cannot access that. I don't have the permission. It's as simple as that. I maintain a database. What can I do? The owner can be the only one who can access the file, right? So Hydra and Tab were kind of like the first capability-based system, which is now used in Linux and Android and many other systems. Quick note here is kind of based on POSIX.1e, which never become a standard. What it means is, well, everyone kind of use it right now, but it's not a standard. It's never officially become a standard. It slices up the root power into distinct area, like network, for example, and each would represent by a bitmap fib, and it gives a fine-grained control over privilege operation by setting this bitmap. So for example, root can go to the network, can go to the file system, right? It separates these two permission out so that I can only go to the network, but not the file system. And I can just go to the file system, but not the network. And to set and reset, just change the 1 and 0 for each operation. And the bitmap become permit, effective, and inheritable. Inheritable means that if I spawn the like child process, right, I do inherit that. This can be applied to each process or each thread. And if I revoke the bitmap, I cannot reacquire it. The process or thread that start with all the it basically start with all the privilege, and then it will decrease the privilege during the execution. This is basically how modern day OS implement the principle of least privilege. You are supposed to do just the only thing you can do, and that's it. I start with all the privilege, and then the OS can kind of reset the bitmap just to things I can do, and that's it, and keep the process running. All right. So here, right? So basically, the thing I want to get out there, like, for example, back in the day, even the ping command would need the root privilege because it does open a network socket, right? Because it does open up the socket. So I don't want to grant the root privilege to everyone. If I want to send a ping command back in the day, I need the root privilege. So what I do is I slice up this privilege into, okay, if you need the network socket, just get the network socket, not the entire root privilege. That's why we have to design this way, right? You have to slice up the power, and then you decrease the power the process can do just to what it has to do. We'll talk about this afterward. All right, this is like other things people use. There's like SIP in Mac OS. That's like Android. Android is a little bit unique because each vendor has their own implementation, so have to design around that concept, because Android will be given to like Samsung, for example, like the LG phone. Even Google has their own phone, right? So that's kind of like unique in a sense. So we'll do that later. So let me go forward and then talk about OS security, which we don't have a lot of time. Let me rush through and see where we are. All right, it's only 20 minutes until the end of this class. Security is basically means that a system is secure if the resource are used and accessed in the way it's intended to do. I intended to just have this particular access right and things like that. I need to make sure that's enforced, and also this is not achievable, right? I can have cracker to attempt to breach security all the time. Look at Cisco, right? So definition, a threat is a potential security violation. A threat is as defined in human language. A threat means that this is a potential thing that can happen that would violate security. An attack is the attempt to breach security. An attack can be accidental or malicious. Malicious means it's aimed to do bad things to your machines. And it's easier to protect against accidental, obviously, against the malicious ones, because the malicious really want to attack you, right? So here are the different categories. So you can have the breach of confidentiality, means that I can have unauthorized reading of your data. I can have the breach of integrity, unauthorized modification of data. When you see the word integrity, means the data changed somehow, so it's modification of the data. Breach of availability is the destruction of the data. It used to be available, now that data is gone. Theft of service, unauthorized use of resource. Denial of service, deny the resource from any legitimate use, right? And you can have different methods to attack the system, right? You can use masquerading to breach authentication, pretending to be an authorized user to escalate the privilege. You can do replay attack, or as is, or like change the message. Like someone sent a message this way, you crack the message, change it, send it to the target. You can have the man in the middle of attack. Basically, intruder sit in the middle, look at the data flow, and masquerade as a sender, and send the data to the receiver. You can hijack a session by intercept any already established session like terminal and bypass authentication. You can escalate privilege, like what happened to Cisco, basically got in, escalate privilege. Here's the thing, it's impossible to have absolute security because, well, new threats is discovered all the time. And how many of you guys write program with no bugs at all? All right. We all wish, right? So it can be really, really hard. So what we have to do is to make sure that if you're attacking my system, I'll make sure that it costs so much. For example, to attack my system, you have to run this thing for like 150 years. By the time I don't have the machine anymore, it'll be rotting somewhere, right? So if I can do that, no one will attack me. For the most part, actually, it actually must happen at, or else, I would say for the most part, have to happen at 4 levels to be effective. The physical level, like in the data center, the server, the connected terminal, the application, the OS, and the network, they all have to be secure. Now I'll add the hardware, so there's way more hardware bugs that can attack your system. Security is also as weak as the weakest link, means that if the OS is weak, I attack the OS. If the application is weak, I attack the application. All right. Human is also a huge risk. Think of your parents. All right. Phishing, social engineering attack, and weak password. Right. And the last thing, can too much security be the problem? I'll actually answer yes. Sometimes, I mean, think about it. What if MUIC asks you to reset your password every month, and the password has to be a mix of alphabet, number, and special character, and at least like 10 letters long every month? Yeah, right. So that's the overhead that comes with more protection, right? Obviously, that's better, right? But yeah, it does have overhead as well. Program threats have many names for that. Anyone heard of Trojan horse? So basically, it's a code segment that run and it misuse the environment. Basically, it exploits mechanism for allow programs written by the user to be executed by other things like spyware that pops up, or like spam that you got by system that already have spyware, right? Like there was a time when like a lot of my friends on, anyone use Skype even now? So I used to use it. The only reason I use it, I can have a US mobile phone. So I basically pay them so I have a mobile phone that are US number, right? Because I still have something over there. But yeah, there was a time when a lot of my friends got like hacked and they spam like random links to me. I'm like, yeah, not replying for sure, block, right? Spyware can be a program that frequently install, like let's say you install a free program and toward the finish button, they say, hey, install this as well. That's kind of bad. Ransomware locks up your data and demand you to pay. You can also have virus. The unique thing about virus is a code fragment embedded in a legitimate program. Like let's say you torrent a game. How can you trust that no one do anything with the executable? I can just add one more function call to like whatever I want to do, right? To open up something I can listen to from your machine. These are self-replicating. That's the key. It's self-replicating. I can infect other people, right? For example, I can write a macro in Visual Basic to reformat your hard disk. Just that, right? Virus dropper is the way to insert virus into your system, and there are many categories which I will list them out so that I can read that. But yeah, it's like you can see that. I'll not go over that list. You can add a virus, for example, on the boot sector. What it means is you're booting, like virus copy the boot sector to unused location and replace. Remember, right? The boot sector is at this location. So what the virus do is, well, throw this away, and then I replicate myself there. Then I can launch whatever I want to launch from the time you open up the machine, not even when the OS runs, right? Malware designed to exploit or disable or damage computer. You can have trapdoors that can even be included in compiler that would trap that kind of would look at your user identifier and will allow you to circumvent security procedures. Think of an actual trapdoor that, like, if you walk, it will like move you to another room, like trapdoor in a game, things like that, right? You can have like logic bomb that is like a code hidden in a program, and it basically wait for certain thing to happen. If that certain thing happen, this thing trigger, right? These all try to violate the principle of least privilege that we talk about when we talk about OS protection, right? So usually would also leave behind some remote control for the attacker that can repeat the process again. One, this is kind of like a textbook example. I talk a little bit about this in system skill. This thing is called buffer overflow, right? So let's say I create a character with this buffer size. What's wrong here? What I do here, right? I take in the input argument from my program, right? And then I copy my argument into the buffer. This thing has size to 56. When I perform a string copy, what if my input is longer than 256 characters? Just keep going up, right? You keep copying, which means that if I just, for example, one thing I can do, I can put in the actual program binary as a part of my input, somewhere, and then I hijacked the return call so that the next line, the program counter points to my program I put in here. Basically, I put my program in the buffer. Then I hijacked. When I return, the program counter will accidentally, by design, point to the new program I put in as an input. We call this a buffer overflow. Because I have a buffer, I want to do a string copy with 256 characters, but I'm not careful with the input. I actually make copies that are longer than 256 characters. It overflows into a space that program counter can access, which means I can write another valid program here and it will run. A code review can help, actually. You can also do a code injection attack. Like system code can have bugs, right? As I said, right? So like how many people write bug-free code all the time, right? Again, code review. It usually allows executable code to be added or modified. Result from poor or insecure programming paradigm, like C and C++, is like super low level, right? You allow to touch the memory location. The goal is to do buffer overflow attack, and it can be run by script kiddie. Basically, someone invents the attack, then open source the attack. Anyone can then write the script to replicate the attack. And here's the injection attack, right? Again, you have the buffer, 256 in size. There's some other variable. And then most of the time, your program has a return address in the stack, right? In the stack. So what can you do? I put in some data. I make sure this go over, right? Like your data is go over, right? Your code go here. Your code go in here. The return address. Let me keep doing the buffer overflow to the return address so it now point to here. Then you're done. because it will run that line, copy the data over, but when it's about to return from that function, instead of going back to the code, it goes to here, right? There's also like 4 layers of security, right? You have the application, OS, network, and physical. There are many types of attack from each type of layer. From the application, you can do code injection like buffer overflow. That means I attack the application, but that's just a main program that I write in C, right? Some design flaw in the program, some logic bugs. The OS, I can try to attack my OS vulnerability, which get patched. That's why it's really important to update your OS, all right? For a network, I can be the man in the middle. I can sniff the packet, I can spoof the packets. I can do the hardware-based attack in the physical level, right? And there are multiple ways you can protect against these attacks. So it's on the right side. Last but not least, because we are wrapping up this part, right? Is spread programming required to exploit the first time? Yes, you have to be really good. Then after the exploit is discovered, right? In many cases, it's like actually being packaged into something that someone that doesn't really like someone that can only write code in Python can then use the package to attack other people. And once that's done, it's basically dangerous. Like look at Cisco, it died. It basically literally attack every other server, right? And depending on the bugs, attack can be executed across the network, right? Because it attacks a machine which can pass the firewall, right? And buffer overflow can be disabled. These days, actually harder, right? You can add a bit in a page table to indicate that this part is not executable. You can also disable execution from the stack because buffer is in your stack. So we can say, hey, if you're running something on your stack, that's not supposed to happen. Two simple ways. A bit in the page table, you're not supposed to run this, or on the stack, say, hey, you're not supposed to run something on the stack. x86 has that. It still have other security exploits that you can attack, right? There are many other more threats. Like these are like attack are common and it moves over time. It can be from like science experiment to like organized crime that would like do ransomware on a hospital database, right? That happened before, quite a while actually. Last thing, Windows, because a lot of people use it, it's like one of the most common targets for the attacks, but now the attack happened on every system. So be careful, even though you use Ubuntu, it doesn't mean that you're attack free, right? Again, in Windows, everyone is the admin. What if you cannot trust, like I'll leave with this, basically. What if you cannot trust the OS? What if you don't trust your own coding? Okay, are you gonna trust engineer from Microsoft or you? Who knows? It's hard to answer that because they're gonna have the security team to check the code and do the code review, right? But as I said, it's hard to prevent against every single attack. From the hardware, there's also help as well. For example, we can have the secure enclave, which is a special hardware designed to protect your data, right? Intel, Apple, AMD, they all have this concept implemented in hardware. Basically, it allows your application to talk to the hardware saying, hey, if I want to access this part of the memory, the hardware has to give the permission, not the OS. All right. We will cover the use case in Android and SIP in the next lecture. These are going to be the content for possible for the exam, right? I haven't made the exam yet, so I don't know what goes in there. Before that, I will leave with like that's also like attack on the hardware. There's like side channel attack, Spectre meltdown, which can attack your CPU. That's also rule hammer. I'll talk about this when we cover the computer architecture part of this course, because we then need to know how DRAM works a little bit more. But then I'll talk about this attack. I'll leave the session for now because it's 11:53. Let me stop the recording.